Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And this video is a continuation of a video series on the mean value theorem. You should have just watched a video on the concept, theorem, and proof of Rolle's theorem. In this video, we're actually just going to use Rolle's theorem. It's actually going to be a somewhat short video compared to the previous one, because whenever you're proving a theorem, it takes a little bit. But in this video, we're just going to go through a couple examples. And fairly typically, more of a rote style example is this one right here. Verify that this function on the closed intervals from 0 to 9 satisfies the three hypotheses of Rolle's theorem. Then find all numbers C satisfying the conclusion of Rolle's theorem. Remember, Rolle's theorem just tells us if you have a continuous function on a closed interval from A to B, and if that continuous function is also differentiable on that open interval from A to B, then there must, and if the endpoints are at the same height, then there must be a point in between where the derivative is 0. Again, first thing you need is f being continuous on the closed interval. You need f prime to exist on the open interval. And you need, finally, f of a to equal f of b. If all three of those conditions are met, then you know there exists a c in the open interval from a to b, such that, that's what that backwards inclusion means for me, such that f prime of c is 0. All right, so let's go ahead and try to do that here. Now, continuity. So this is kind of an easy one. So a lot of students get thrown off by this style of question, but really all I need to state is that our function is continuous on its domain. Remember, we had a theorem a long time ago, way back when we were dealing with limits, and somewhere when we were dealing with limits, we dealt with continuity of functions, and at some point within that discussion of continuity of functions, we talked about the fact that, and I called it the generalized direct substitution property, but in reality, it is a theorem that's very useful for this section of material specifically, which is that most of our functions, if not all of our functions that we're very familiar with, are continuous on their domains. Polynomials are continuous on their domains, radical functions, rational functions, trigonometric functions, exponential functions, and logarithmic functions. They are all continuous on their domains. And so now when somebody says or asks, is this function continuous? All I need to state is, or cite, is that theorem. These functions are all continuous on their domain, and the domain of this function here is 0 to infinity, including 0. And so therefore, this function's continuous from 0 to 9. That's all you have to do. If you don't do that, you can't use Rolle's theorem. That's just an important point to make. A lot of students on exams tend to kind of gloss over this step. They don't say it. It's the easiest step in the world, but for some reason they just forget it and move on. You can't do that. So we need that continuity to be stated. So our first condition is met. Our second condition is we need the function to be differentiable. And so the best way to do that is to find what f prime is. And you're going to have to do that anyway. You'll see in a moment why. So f prime of x here is 1 over 2 root x minus 1/3. And that, you can see, exists on the open interval 0 to infinity, right? Because you can't include 0 because you'd be dividing by 0. So this implies f prime exists on the open interval 0 to 9. That's very specific because I need it to use Rolle's theorem. I need it to be differentiable on the open interval. It could be differentiable at the edge point too, but that's not necessary for Rolle's theorem. So you really go with the loosest restriction you can. And then finally, third condition. I want to look at these edge points here, 0 and 9. I want to see what the function values are at x equals 0 and x equals 9. So f of 0, go ahead and zoom out. F of 0, well, that's 0. You can easily see that. And f of 9 is square root of 9 minus 1/3 of 9, which is 0 again. So f of 0 is equal to f of 9. Great. We have all three conditions met, which implies, by Rolle's theorem, there is some point between 0 and 9 where the derivative is 0. I'll just write that down. All right, so we have that stated, and I should say by Rolle's theorem, because that's kind of nice to cite why this statement is true, and some people might need that reminder, so I'm just going to say by Rolle's theorem. All right, so let's go ahead and find that value of c. What is the value of c such that its derivative at this function's derivative at c is going to be 0? Well, luckily we took the derivative. It's right there. So I'm just going to insert c and set it equal to 0. So I'm going to solve, zoom in a little bit. F prime of c is equal to 0. F prime of c is just this 1 over 2 root c minus 1/3. And that's equal to 0. And you get that that implies 2 root c is equal to 3. Or in other words, c is equal to 9/4. And there you go. There's only one value here where the derivative is 0, but that's okay. That's all we need. Sometimes you'll get 2 or 3 places where the derivative is 0. So anyhow, this implies f prime at 9/4 is equal to 0. So that's a full kind of rote typical example of using Rolle's theorem. You're handed a function, you're asked, hey, is there a point in between 0 and 9 where the derivative is 0? And it's worthwhile to, before calculating that, to determine if that point can even exist. Now we get to the real reason why I love Rolle's theorem. Rolle's theorem has a few really cool uses, but this is probably one of the best uses, is to prove that a function has exactly one real root, or an equation has exactly one real root, or something like that. So let's talk about how this is done. And we're going to do this as if it were a courtroom drama. The reason why I'm doing it this way is because of the way we're going to prove that this function has exactly one real root, and that root is between -1 and 0. It is the proof style we're going to use is called the proof by contradiction. And there are a few things that I need to kind of set up before we get there. This specific style of proof is called an existence and uniqueness proof. Existence and uniqueness ends up being a huge thing in mathematics. When you want to prove that, for example, in this case, that this function crosses the x-axis only once, well, you have two jobs. Prove that it crosses the x-axis. That is, there exists a point where it crosses the x-axis. And then, second job, prove that it only does that once. That is, the crossing point is unique. That is existence and uniqueness. So there's two jobs here. And a lot of proofs in mathematics involve an existence and uniqueness argument. They're two separate parts to the proof. So, how are we going to do this? Thus begins the courtroom drama. Ladies and gentlemen of the jury, it's my job to prove to you that this function crosses the x-axis only once. That is, it has exactly one real root. Not only is that my job, but I want to convince you that it's crossing the x-axis between x equals -1 and x equals 0. Now, I hope you follow my logic in this argument as I present to you undeniable evidence that this is true. I'm going to build a case that cannot be refuted, that will be locked down, solid, tight. First of all, let's discuss the fact that it does cross the x-axis. And this, ladies and gentlemen, will be our existence portion of today's courtroom drama. I hope you'll all agree that our function is continuous. In fact, let me write that down for you. F is a polynomial, and polynomials are continuous on the real number system. That's right, gentlemen in the back of the room. That's what that symbol means, the real number system. So we know that our polynomial is going to be continuous, or our function is going to be continuous for all real numbers on the real number line. Specifically, it will be continuous between -1 and 0. So maybe I should write that down as well. Now I know what you're thinking, ladies and gentlemen. What does that have to do with proving that this function must cross the x-axis? Oh, by the way, if you are new to the world of mathematics, when I say that a function has a root, that means it crosses the x-axis. I'm using my dramatic voice. Well, I hope you forgive my assumption that you know how to evaluate a function, but if you consider f evaluated at -1, and my poor handwriting skills, f at -1, you will see that our function becomes -1 minus 4, which is -5, minus 3, which is a -8, plus 5, which is a -3. And I hope everybody in this room agrees that is a negative number. If you don't agree with that, I ask the judge to remove you from the jury box. Also, at the same time, I hope that everybody in the room can also agree that f at 0 is going to be 5, which is a positive number. Ladies and gentlemen of the jury, I think that you would all agree with me. Our function has gone from a negative value to a positive value. Moreover, our function is continuous. So, ladies and gentlemen of the jury, I submit to you by the intermediate value theorem that our function must have crossed the x-axis at some point between -1 and 0. This is when somebody in the audience says, but wait a second, I don't know what the intermediate value theorem is. And I say, well, you should watch my video on the intermediate value theorem. If you have a continuous function, it goes from a negative to a positive. It had to cross all points in between, specifically the x-axis. And they go, oh, okay, all right, perfect. But some astute observer within the jury box says, well, that doesn't prove there's exactly one place where it crosses the x-axis. And so me, as the attorney in charge of this argument, or the lawyer in charge of this argument, says, of course, what an astute individual you are. Let's go ahead and prove that there's only one such point where it crosses the x-axis. Ladies and gentlemen, this is when we start our uniqueness portion of this trial, so let me go ahead and write that down. Now, before I continue, I just want to say the way I'm going to argue here is a lawyer's argument. It's called a proof by contradiction. A proof by contradiction is what you do when you really want to confuse somebody verbally, but it's also a very powerful way of proving things in mathematics. The way it's done, pretty much, is this way, where you say, oh, you're making some claim. Like somebody says, I believe this is true. Or maybe you're saying that. So suppose you say, I really believe the sky is blue. And your friend says, well, I know, it's not. The sky is, green. And you say, well, okay, let's suppose it's green. So you basically suppose the opposite of what you're trying to prove. And then when you make that supposition that's opposite of what you're trying to prove, something logically will break. And then you have to follow your argument back to find out where you made an assumption. And that assumption is your weakest link, and that assumption should have been wrong. So that's a proof by contradiction. It's a great way to argue. And it's sort of like when your friend, if somebody's arguing with you and they say one thing, you say the opposite, right? Oh, I say this is true. And you say, no, that's not true. And they say, I swear it's true. And you say, well, okay, let's suppose that what you're saying is true. Then this would happen. Then that would happen. Then the world falls apart. And they go, oh, I never really thought about it that way. Yeah. So that's a proof by contradiction. All right. So let's go ahead and prove uniqueness by contradiction. So again, I'm the attorney in charge. Some other attorneys in the room, and they're saying, well, this one guy, this mathematician here, can't prove that there's only one root. I'm saying there's more than one root. And I come up and I say, ladies and gentlemen of the jury, I'm telling you right now, there's only one root. But you know what? Let's follow Mr. Other Attorney's logic. Let's suppose there's more than one root. And ladies and gentlemen of the jury, I wrote that in red so that we can see that assumption for the rest of this argument. Now, I hope you know, ladies and gentlemen of the jury, that f, as we stated earlier, is continuous on that closed interval from -1 to 0. So f is continuous on -1 to 0. And everybody nods their head because, well, we had stated it earlier right above. F is continuous on -1 to 0. So they all kind of nod their head and they say, yeah, okay. And I say, well, moreover, ladies and gentlemen, the derivative, which is actually 7x to the 6th, let me just zoom out for you, ladies and gentlemen of the jury, so you can see the original function. You can see it up above, and you can see that it's derivative right there, because everybody in this courtroom and the jury themselves they're all trained in calculus. You happen to know the derivative is 7x to the 6th plus 20x to the 4th plus 3. And everybody nods their head. And you say, of course, that derivative, because it's a polynomial, exists on all real numbers. And they say, of course it does. And then you just verify with the jury. Ladies and gentlemen of the jury, in that black ink there, have I told you any lies? They shake their head. No, you haven't. You say, okay, great. And would you mind if I restrict down the interval over which I'm talking about the existence of the derivative to just be from -1 to 0? So that is, f prime exists also on the open interval -1 to 0, since it exists for all real numbers. And they nod their heads and they say, of course, yeah, that's perfectly fine. This is a really good jury. They're very smart. Good calculus savvy jury. And you say, great. Well, ladies and gentlemen of the jury, I think that we also have said something earlier about this. Let me just see what I could do here for you. And you grin because you know where you're going to go. And you say to the jury, well, ladies and gentlemen of the jury, since we're supposing that, I don't know why I use that accent, by the way. Since we're supposing that our function has more than one root, there must be 2x values for this function where it crosses the x-axis. It could be a bunch, but for right now, y'all agree with me that we have at least 2 places where it crosses the x-axis because we're assuming we have more than one root. And they all nod their heads and they say, yeah, of course. That's what the other attorney would want you to believe. And they say, yes, yeah, okay. Since we have assumed f has more than one root, on that interval from -1 to 0, that is, there must exist C1 and C2 such that f of C1 equals f of C2, which equals 0. And they all nod their heads and they say, of course, yeah, we've assumed that there's 2 places where that function hits the x-axis. Ladies and gentlemen, this is not really a rigorous part of my argument, but I just want to draw out a picture so that y'all can agree with me that you have said the following. We have this interval from -1 to 0, and we have this continuous function that is also differentiable, and you say that there are 2 points where we cross the x-axis, and they all nod their heads and they say, yes, of course. That's exactly what the other attorney wants you to believe. Well, let me tell you what hullabaloo or what hocus pocus that attorney is trying to sell you. Because I'm stating to you right now, I've given you a continuous function on a closed interval. I've also given you a function, the very same one, whose derivative exists on the open interval from -1 to 0. And we all have supposed that the function attains the height of 0 twice within that interval. Well, by a really good theorem called Rolle's theorem, there must be a point in between C sub 1 and C sub 2 such that the function in question has a derivative equal to 0 at that point. So right here, f prime at c should be 0. And everybody nods their head. And they say, yes, let me write that down for you folks. There we go. We got that written down so that everybody can see this in the courtroom and they all know what's going on. And everybody nods their head and they say, yes, of course. Yeah, that looks great. And then me being the Southern lawyer, geez, I don't know where I'm getting all this. I'm just making this up as I go along. But you get the idea so far. Then the lawyer, me, turns to the attorney and says, this is where I got you. And you don't even know you've been caught. And everybody in the courtroom is now riveted. They're leaning forward. They're like, what is he going to do next? Ladies and gentlemen of the jury, I'm going to tell you that other attorney doesn't know come here from Sikkim. I'm going to tell you that he has made a flaw in his argument. Because we have done said that this derivative will become 0. You agree with all my logic, right? Everything we've written out here, except for that red ink, everything we've written out here is perfect. We got a continuous function. It's differentiable. Since we've assumed that we have more than one root, then we have 2 points on our curve that have the same height. By Rolle's theorem, we know there's some point in between C1 and C2 where the derivative is 0. Ladies and gentlemen of the jury, I say to you, this cannot happen because this would imply that 7x to the 6th plus 20x to the 4th plus 3 would have to be 0. And they all nod their heads. Ladies and gentlemen, if you can't do mathematics like this, then I'm sorry to tell you, you need to go back to school. Because 7x to the 6th is greater than or equal to 0. 20x to the 4th is greater than or equal to 0. And 3, well, doggone it, that is always 3. So therefore, f prime of x on that given interval, actually on any given interval, is always going to be greater than or possibly equal to 3. But this contradicts the fact that the other attorney is telling us that f prime can become 0. And I put in a little but there just so that you could see that I'm saying this is where the contradiction occurs. So this contradicts the result that the derivative must equal 0. The derivative can't equal 0, ladies and gentlemen, so there must have been a flaw in our logic. Now, you have all agreed with me that my black ink here is all solid, tight logic. So where could I have made an assumption or a supposition that's incorrect? Well, ladies and gentlemen, in that red ink is the only supposition I ever made, and that's a supposition that the other attorney here from good old New York City is trying to tell us is true, that our function has more than one root, on -1 to 0. Thus, that supposition is flawed, ladies and gentlemen, and it must be incorrect. Hence, ladies and gentlemen of the jury, f cannot have more than one root on -1 to 0. And we have proved that that root that we found originally, we have shown there's already 1 0. From our existence conversation, we know this function crosses the x-axis. And now we've shown it can't have more than one place where it crosses the x-axis. Thus, we have proven the statement. It has exactly one place where it crosses the x-axis. Ladies and gentlemen, in Latin, quod erat demonstratum.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.